India's execution of Operation Sindoor marks a watershed in modern air warfare, propelled by its doctrinal clarity, technological superiority, and operational discipline. The Indian Air Force's deployment of the Dassault Rafale multi-role fighter, integrated with the Meteor Beyond Visual Range air-to-air missile, fundamentally altered not only the tactical landscape, but also the strategic calculus of regional adversaries. While speculation persisted regarding the actual wartime loadouts of Indian Rafales during Operation Sindoor, and rumors swirled claiming that Meteors were not flown on combat missions, technical briefs, procurement and readiness data conclusively confirmed that the Indian Air Force possessed in excess of 200 operational Meteor missiles well ahead of the hostilities, with all assets on high alert status. This revolutionary missile, developed by MBDA, is widely recognized as the world's most advanced BVR air-to-air weapon. Operation Sindoor signified not merely a test of force, but a masterclass in the scientific and technological evolution of air combat, with the Indian Air Force demonstrating the depth of modern aerospace power through both doctrine and unmatched hardware. At the very heart of this transformation was the Meteor Beyond Visual Range air-to-air missile, a product of meticulous European collaboration and advanced research, which enabled India to wield a missile with capabilities surpassing anything previously fielded in the region. The details underlying Meteor's effectiveness are rooted in its core design choices, manufacturing precision, and the integration processes that bridged platform, pilot, and weapon in a seamless digital ecosystem. Meteor's most distinctive design innovation is its variable flow solid-fuel ramjet engine, a leap beyond traditional rocket motors. Upon release, the missile undergoes a two-phase propulsion regime. First, it is launched from the host aircraft, typically the Rafale in the IAF's case, by an initial solid booster phase that brings the missile quickly to supersonic speed, minimizing drag at low altitude and rapidly clearing it from the launch tub. As it transitions through denser atmospheric layers to cruise altitude, the booster stages separate, and a pressure-activated intake system deploys, allowing air to be ingested and ignited with onboard solid fuel in the ram combustor chamber. Combustion efficiency is carefully regulated by a digital control unit that orchestrates thrust modulation, giving Meteor not just high initial acceleration, but the extraordinary ability to sustain and, if required, increase velocity throughout each critical engagement phase. This ramjet is a masterwork of energy management, constructed from heat-resistant alloys and ceramics selected for both their lightness and thermal durability. The result: a missile that neither wastes fuel in the early phases nor loses the critical endgame energy, essential for intercepting modern fighters executing sharp brake turns in the missile's approach window. The thermal signature is also modulated by careful nozzle shaping, making lock-on by infrared-guided countermissiles or tracking radars more difficult, thereby increasing survivability against modern countermeasures. Aerodynamically, Meteor's slender dart profile is shaped for minimal drag and maximum directional stability at high Mach speeds. The canard-actuated control vanes, precisely stamped from composites, are positioned to optimize controllability during both low and high-altitude interception geometries. This design is tuned through thousands of hours of wind tunnel testing, CFD simulation, and live launch telemetry, data which is continuously fed back into production and software upgrades. The guidance fins, actuated by electromagnetic motors drawing power from an internal thermal battery, respond to missile autopilot and mid-course correction signals with millisecond precision, enabling rapid course adjustments in response to live data link commands or abrupt target maneuvers. Meteor's active radar seeker is built upon X-band AESA, active electronically scanned array architecture, featuring gallium arsenide GaAs and gallium nitride GaN, modules miniaturized for missile use. This seeker is capable of track-while-scan operation, allowing the missile not only to search for and lock on to its primary target, but to maintain awareness of potential secondary or decoy contacts. The radar's digital signal processor executes advanced clutter rejection, exploiting Doppler shifts and frequency agility to distinguish between real targets and even the most sophisticated chaff or electronic decoys. Experimental testing in Europe, and with IAF during integration trials, demonstrated Meteor's resistance to soft kills from both ground-based and airborne jammers, validating design choices in both hardware shielding and adaptive software. The Seeker's power and intelligence are complemented by the all-important data link, which bridges the missile to the launching fighter and, via secure tactical networks, to Indian AWACS and command posts. Using NATO standard MIL STD 1760 interface protocols adapted for Indian-specific cryptography, the data link provides gigabit-class throughput for command updates, target discrimination, and battle management. This allows a missile launched early in the engagement to be retasked mid-flight if the tactical picture evolves. For example, if a target turns away or a higher priority threat emerges in the missile's path. Meteor's digital brain, the flight control computer, represents decades of miniaturization and software advancement, running real-time mission code that fuses seeker data, platform instructions, inertial sensors, and home-on-jam algorithms. In practice during Operation Sindoor, this allowed Indian Rafale operators to launch Meteors in salvos, then dynamically assign each missile to priority targets set on the evolving air battle, maximizing missile usage and engagement efficiency. Crucial to safety and lethality is the missile's warhead and fuse technology. Meteor employs a high-density blast fragmentation warhead, engineered for optimal lethality against both heavily protected aircraft and light, highly maneuverable jets. The dual-mode look-down, shoot-down, and proximity fuse trigger is programmed pre-flight for altitude, anticipated closure rate, and expected radar cross-section signature of the target class. In the event of a miss or lost target, an intelligent, safe self-destruct protocol is automatically armed, preventing friendly fire risk or unintended ground impact, a hard lesson from past BVR conflicts globally. Meteor's manufacturing process is an exemplar of modern aerospace quality control. Each component is subject to multi-tier supplier certification, X-ray microstructure examination, and robotic assembly line checks. LMS, Life Management System, tags every missile for digital tracking, oversight, and predictive maintenance, allowing IAF logistics to ensure no missile ever exceeds prescribed storage cycles, battery life, or software compatibility windows. The transfer to India involved extensive technology audits and train-the-trainer programs, with MBDA providing live-fire launch support and joint telemetry analysis during integration exercises. The operationalization of Meteor within the IAF demanded rigorous systems integration and aircrew retraining. Rafale fleet avionics were patched with new fire control logic to harmonize with Meteor's kinematic model, and the Spectra YEO suite received bespoke data libraries for the missile's unique frequency hopping and sensor profiles. EMC, electromagnetic interference compatibility, trials simulated hostile environments to guarantee zero crosstalk or functional degradation. Indian YEO officers drilled pre-mission ECCM playbooks, adapting both offensive and defensive roles by synchronizing jamming patterns, decoy deployments, and missile flyout algorithms. The integration team simulated composite threat arrays, from legacy monopulse radar threats to multiband MANPAD pop-ups, ensuring the missile's in-flight signature could evade or overcome layered electronic and kinetic defenses. During Operation Sindoor, these preparations translated directly into battlefield results. When Indian Rafales and supporting assets sortied in mixed strike and air dominance packages, the battle network was alive with telemetry. Each missile launch was plotted, incoming threat vectors mapped, and friendly formations shaped to maximize both standoff reach and mutual support. When meteors were fired at Pakistani formations, the Indian command node maintained continuous awareness of missile status, real-time tracking updates, and post-missile launch environmentals, allowing for transparent after-action reporting and rapid retasking, a level of digital integration previously unseen in South Asian air history. Scientifically, Meteor challenged long-standing assumptions about BVR dominance. Unlike earlier doctrine, which often assumed diminishing kill probability as range increased. Meteor's ability to sustain Mach-class speed and guidance integrity led to a paradigm where even retreating, jinking adversaries remained highly vulnerable once the no-escape zone was penetrated. This altered both enemy and friendly aircrew psychology. Pakistani pilots, upon realizing their missile warning receivers triggered far past their own BVR range, could not reliably defeat the inbound threat through traditional brake turns or chaff, eroding confidence and compounding tactical disadvantage. The IAF's logistics pipeline was recalibrated to ensure Meteor's operational tempo could be maintained indefinitely if required. Advanced modular storage units, climate-controlled and shock-damped, housed missile arming stations at forward bases, while digital inventory tracked every round from shipment to storage through loadout and firing. Resupply was coordinated via secure digital orders, with MBDA maintaining a remote support liaison system capable of software refreshes and technical troubleshooting without risk of data compromise. Ground crews received cross-training in fuse programming, avionics data transfer, and maintenance cycles to optimize throughput and eliminate bottlenecks during high-surge sortie periods. In practical use, Meteor's philosophy of fire and update gave rise to innovative engagement tactics during Sindoor. Indian Rafale squadrons devised new BVR maneuver patterns, such as fan launches, where a single flight could launch missiles in a spread, then update targets mid-course based on enemy response, and barrage denial, using Meteor to block likely ingress corridors even before enemy aircraft reach their attack or escape threshold. These patterns, modeled in high-fidelity digital simulators prior to the operation, were validated live in some of T. He region's most contested skies. With Meteor's extended reach and robust ECCM, friendly assets could serve as forward sensors or decoy generators, while Rafale operators queued launch windows from standoff distances, delegating kill and surveillance tasks in real time. The air campaign became a tapestry of kinetic, electronic, and networked contest, the technical maturity of Meteor allowing human operators to orchestrate, rather than merely survive, the chaos of modern air battle. No discussion of Meteor's impact would be complete without addressing the missile's feedback loop in terms of future Indian developments. Indian defense scientists and engineers, working in both DRDO and aerospace industry partnerships, used telemetry and post-firing performance data from Sindoor to refine indigenous programs like Astra Mk2 and NG-ARM, next-gen anti-radiation missile. Meteor's integration protocols, digital fire control, and safe handling regimes gave an invaluable template for Indian missile R&D, targeting compatibility with an even wider range of platforms, ensuring sovereign, scalable access to BVR technologies moving forward. In summary, Meteor's debut under operational conditions in Operation Sindoor was more than a battlefield advantage. It was proof that scientific ingenuity, engineering discipline, integration rigor, and tactical innovation can produce an insurmountable whole. For the Indian Air Force, its adoption meant the ability to shape the engagement envelope on its own terms, denying adversaries the comfort of symmetry and dictating not only if, but how and when battles were fought. Combined with the S-400's ground-based reach, multi-layered network warfare, and a relentless logistic and training effort, the Meteor stands, technically and historically, as the benchmark for BVR missile excellence, its ripple effects likely to shape doctrine and decision-making for a generation across Asia and beyond. IAF Battle Management fused S-400 target acquisition with airborne Rafale and Su-30 sensor inputs, creating a redundant and agile air defense grid. Several Pakistani jets and combat support aircraft attempting to break through this layered network were engaged and destroyed over contested territory, further degrading the PAF's operational tempo. The dynamic integration of S-400 surface-to-air and Meteor air-to-air zones essentially funneled Pakistani intrusions into predictable, lethal engagement traps, ensuring absolute air denial without Indian aircraft entering a threat envelope. Contrary to adversarial claims and later propaganda, India suffered zero aircraft or pilot casualties throughout the operation. All deployed fighters returned base intact, a testament not merely to weapon system superiority but to rigorous pilot training, disciplined command and control, and a robust joint operations doctrine emphasizing force preservation, alongside inflicting strategic attrition. In contrast, the Pakistani Air Force sustained significant losses. The aftermath of these combined arms operations saw the PAF retreat into a purely defensive stance, its surviving high-value assets forced to operate from deeper within Pakistani airspace, severely curtailed in both offensive and defensive utility. Beyond air-to-air losses, Operation Sindoor was characterized by the systematic targeting and destruction of Pakistani airbases, radar networks, and command and control infrastructure. Indian precision-guided munitions, released from various platforms under extensive Meteor and S-400 provided air cover, achieved substantial damage against hardened aircraft shelters, radar arrays, and operational headquarters. The prevailing Indian operational doctrine, synergizing long-range missile dominance, high-velocity kinetic and electronic suppression, and rapid tempo sorties, proved overwhelming. By the operation's close, real-time satellite imagery and intelligence assessments confirmed the degradation of multiple key Pakistani airfields and the incapacitation of several radar and early warning networks. In practice, the Rafale Meteor combination enabled deep strike and interdiction at standoff ranges, affording Indian pilots unmatched survivability while inflicting damage on critical enemy assets. This campaign validated a generational leap in Indian air power, demonstrating for the first time that ownership of advanced Western BVR missile technology offered a conclusive asymmetric edge over both Pakistani and potentially Chinese adversaries. Indian pilot interviews and mission debriefs post-operation underscored the confidence with which targets were engaged at long distances, and the seamless swing between air dominance and strike roles made possible by both the Rafale's multi-role versatility and Meteor's fire-and-forget logic. The combination afforded by Meteor's longest, no-escape, zone, mid-course guidance with real-time target updates, and advanced end-game ECCM capabilities left no effective counter for adversary aircraft not operating under the cover of heavy ground-based jamming or outside the Meteor's reach. The result was a shift in regional air doctrine. Close-range dogfighting was, for the first time, rendered strategically obsolete as Indian pilots systematically denied adversaries the opportunity for even medium-range contestation. In parallel, Indian logistics and operational readiness ensured sustained Meteor missile availability throughout the operation. Despite the intense pace of combat, rapid rearming and forward deployment logistics guaranteed that Rafale squadrons were never left without full offensive missile loads, a critical advantage in maintaining a persistent threat umbrella. India's deep stocks, exceeding 200 operational Meteor rounds, assured multiple waves of BVR launches, overwhelming any Pakistani attempt to exploit possible magazine exhaustion or sortie pause windows. This robust logistics tail, combined with indigenous efforts to accelerate the Astra Mk2 BVR missile program, ensured continued domination even as hostilities neared conclusion, and future conflicts would only further increase the indigenous share of India's air weapon inventory. The outcome of these combined technological, doctrinal, and logistical advantages was clear. Pakistani air operations were rapidly relegated to local air defense and rear area support, with deep strike options entirely denied. IAF offensive teams dictated conflict tempo, forcing Pakistani reactions, while Indian platforms operated under overlapping bubbles of Meteor air-to-air and S-400 surface-to-air coverage. Indian airplanners fused live feeds from airborne and space-based sensor platforms into the command network, allowing for rapid engagement cycle closure and near-perfect threat anticipation. This real-time, network-centric battle management not only preserved the entire Indian inventory of aircraft and pilots, but also ensured that every sortie produced measurable attrition on the adversary's warfighting capacity. Official Indian statements, while diplomatically careful not to divulge granular operational details, repeatedly emphasized that Pakistani fighter losses were a combination of air-to-air kills and long-range intercepts by the S-400 Triumph system. The absence of Indian losses, confirmed independently by international observers and satellite data providers, contrasted starkly with recurring Pakistani claims of downed IAF jets, for which no material proof was ever presented. India's comprehensive performance during Operation Sindoor has already triggered significant doctrinal shifts across regional air forces. The proven effectiveness of deep penetration Meteor BVR engagements, the seamless integration of S-400 family interceptors, and an advanced air fleet that returned unscathed, all have recalibrated the regional cost-benefit equation for any future air power contestation. Concurrently, the Indian defense establishment has expedited efforts to increase the Meteor inventory, institutionalize advanced BVR combat training at the squadron level, and accelerate indigenous missile development programs such as Astra Mk2 to further hedge against future supply chain and technological risks. In conclusion, the unassailable record established by Indian Rafales and the Meteor air-to-air missile in Operation Sindoor, demonstrated by the decimation of adversary air power, the preservation of every deployed IAF platform, and the destruction of critical Pakistani command infrastructure under the shelter of robust standoff engagement envelopes, serves as definitive proof of the country's qualitative and doctrinally innovative air power ascendancy. With its integration of advanced Western missile technology, indigenous operational innovation, and flawless execution under fire, the Indian Air Force has not only set the benchmark for aerial warfare in the region, but also established a template for premium, no-compromise air defense and offense for decades to come. Every dimension, tactical, technical, and strategic, of Operation Sindoor reinforces the singular conclusion: India's investment in Meteor-armed Rafale squadrons and layered S-400 coverage delivered an overwhelming victory, fundamentally altering the regional balance of air power and rendering obsolete the conventional paradigms of subcontinental aerial conflict.